Ladies and gentlemen, welcome to week 7 of BLDG 1012. This is your first online lecture after all the crazy things that have been happening due to the virus. Now, to make sure that you guys don't get bored, I'll try to minimize as much as I can the recording time. Now, this week is the final week where we'll talk about concrete. And specifically this week, we'll be covering concrete mix design procedure. So the method that is adopted in order to design your normal concrete mix. Now, the learning outcomes for today, we have two main learning outcomes. The first learning outcome is to make sure that you guys are able to design normal concrete mix. And the second learning outcome is to ensure that you can use the BRE guideline. Basically, BRE is the British Research Establishment guideline, and this is used as a standard reference for concrete mix design. It's a very easy guideline to use, and I've already uploaded the guideline as a PDF document onto Moodle, so please do check it out. But I'll basically be going through the use of the guideline and the process that is adopted to design your concrete, your normal concrete. Now, let's start off with station 1, of course, as usual. This week we have around 7 stations to cover. The first station talks about definitions. So, what are some of the definitions that you need to be aware of? Well, to be honest with you, it's just one single definition, and that is what is concrete mix design. Technically speaking, when we refer to concrete mix design, we're referring to the process of selecting and proportioning your constituents in concrete. Now, remember in previous weeks, we talked about the constituents of concrete, and we discussed cement, we talked about water, we talked about the aggregates, and you guys also covered additives or admixtures. Now we need to select appropriate proportions for each of these constituents, and that's what concrete mix design is about. Now the mix needs to be designed in a way where you achieve a particular workability, a particular strength, and a certain level of durability. And this is all determined based on your concrete structure. So a high-rise building made out of concrete will have different workability requirements, different strength requirements, and different durability requirements compared to, let's say, for instance, a concrete pavement. Okay, so in terms of the selection and the proportioning of materials, what do they depend on? Well, there's a number of things that you have to consider. Number one, the structural requirement, i.e. the strength of concrete that is required for your project. Number two is the environmental exposure, and we talked about how cement as a product is a very energy intensive product, i.e. producing it requires a lot of energy. So that, you know, the more strength that you require, the stronger the cement that needs to be used in the concrete mix. And this is something that you have to consider because it will inevitably have impacts in terms of how much energy will actually be expended to produce such cement. Job site conditions, so access, for example, to your construction site. How easy is it to transport the concrete and then pour it on your construction site? And then finally, the characteristics of the available raw materials. So depending on the region that you're in, you get different raw materials, and these can impact the overall characteristics of your concrete mix. Now, in terms of the concrete mix design itself, some of the factors that we need to consider: compressive strength, of course, the workability of the concrete, and then the type of aggregates. And these are basically considerations that are outlined in this BRE guideline, so the British Building Research Establishment. And it lists down the different stages that need to be followed when you when you want to produce a certain design of your normal concrete mix. Now, I stress the word normal over here because we're not talking about any concrete mix that is special, i.e. any concrete mixes that have additives or admixtures that need to be placed because of certain requirements of your project. I'm just talking about your normal concrete, no admixtures, no additives. So there's no specific properties that we need to modify, and it's just simply a water to cement ratio that you need to design, the cement content, and then the aggregates and how to proportion them between fine and coarse. That's basically how that's basically the parameters that are involved in your normal concrete mix. Now, station 2 for this week, I'll talk about the inputs and outputs of the procedure. So the process of designing your mix can be split into these 5 stages that you see in front of you. So stage 1 is related to strength of the concrete mix, and as an output of stage 1, you will get your free water to cement ratio. Stage number 2 is associated with workability of your concrete mix, and the output is your free water content. And then stage number 3, you combine the results of both previous stages to get your cement content. Stage number 4 determines the total aggregate content, and then finally stage number 5 is where you proportion your aggregate content into fine and coarse. So it's not a very difficult procedure, to be honest, and it's as long as you're aware of what takes place at each stage, it's a systematic process. So let's talk about the input data that's required before you start the process. You need to know, and this is information that you get from your client. So you need to know what the characteristic compressive strength is. You need to determine what the minimum and maximum water to cement ratios are. The minimum cement content that's desired by the client, the slump that is desired, and the maximum aggregate size. Other inputs that need to also be determined, possibly, so these are labeled as additional information. You might need to determine the aggregate types that the client requires, the different aggregate densities, of course. So various aggregates, like we discussed previously, they have different densities. So you need to be aware of the densities of these different aggregates. How fine your aggregate is, level, and that's related to your sieve analysis, of course. Data that controls the compressive strength. So remember, this is all done in a lab setting. So when you produce your concrete mix, you need to take samples to ensure that you get the specific strength that is desired across various samples, and that's how you can control for variability in strength, and that's related to the defective rate. So a defective rate would usually be specified to outline how variable your concrete strength needs to be. Now, the less variable the strength, the better, because the less variable the strength, it means that your design, if you design, let's say for example, 100, if you take 100 samples from a particular concrete mix design, it means that if it has a low variability, it means that in most of these samples, so let's say for example 96 out of 100 of these samples, you'd have no variability in strength. So your strength would be exactly what you require, and that is what's designed. Okay, so that was for the input data. In terms of output data, your output of the process of the full procedure looks something like that. So you'd specify in kilograms per meter cubed, of course, how much cement will be available. So this is just, these numbers are just an example of one of the designs. So water is 180 a fine aggregate 615, and then you have two types of coarse aggregate, and these are 360 and 825 respectively. So that's just an example of the output that's expected from this process. So the easiest way of explaining the process is actually going through an example. Now, I will be using, as I mentioned earlier in the lecture, I'll be using the BRE guidelines, which you guys already have access to on Moodle. And it's very easy to use, to be honest. It's just, like I said, it's a systematic process. As long as you understand what happens at each stage, you just do one single example and then it'll automatically become easy for you to solve any of these mixed design problems. So let's start just looking at this example over here. Now, do not worry a lot about what's mentioned over here, because when you open up your BRE guidelines, you'll notice that it's split into different sections, and these are basically references to these different sections. So in the next couple of slides, I'll make sure that I refer to these sections, and I'll take screenshots of where exactly we will be focusing on in terms of the material provided in the guideline. So these are labeled 1 to 6. So this is the information that we talked about, input information that you get from your client. Now we've got a characteristic compressive strength of 30 newtons per millimeter squared. And that's just basically MPa, equivalent to MPa, so 30 MPa at 28 days. So the client desires to reach that strength, 30 MPa at 28 days. And the defective rate that's specified is pretty low, 2.5%. Again, don't worry about the K for now. I'll explain that later. The class of your Portland cement is mentioned as 42.5. The slump that's required, maximum aggregate size, maximum free water to cement ratio, and the minimum cement content. So everything over here is specified by the client. There's also this paragraph over here that talks about the fine and coarse aggregates. They need to be uncrushed, so it's specified by the client. The relative density is unknown, and hence you'd assume 2.6, as stated in section 5.4 of your BRE guideline. And your free aggregates, after conducting a sieve analysis, it was revealed that 70% pass a 600 micrometer sieve. So these are all information that are provided to you by your client, and you're required to come up with the concrete mix design. Okay, so the process is made very easy in the BRE guidelines because of this form that you see in front of you. So you see that this form is split up into 5 stages, 1, 2, 3, 4, 5. These are the 5 stages that are involved in your concrete mix design. And all you have to do is just follow these steps one by one. Now this column over here refers to sections in the guideline where you need to refer to. Now the beauty of the guideline is that if you have a look at the PDF file, the PDF file of the guideline that I've uploaded onto Moodle, if you click on these different hyperlinks that are sort of highlighted in a box, it takes you directly to the section that you require. And that's just to make your lives easier. So do check it out on the PDF file. So basically our design process is going to be filling out this form, and I'll show you how to do it. The whole process is split into 5 stages, as I said. So let's start off with stage number 1. This is station number 3 for this week. Stage 1 starts with the characteristic strength. So this is the strength that's desired by the client. So 1.1 in the form, you got to fill out in this dotted line, or I should say on this dotted line, the strength that is desired, and we can just extract that directly from the information. So I've listed the information again, the input information that you got from your client over here. So your 30 goes here. It's desired at 28 days, and then the defective rate that's mentioned by the client is 2.5%. So this is all information that will be needed for the later stages, for the later steps in stage 1. So first step, 1.1, you just list down these three values that we obtained directly from the client. Let's move on to step 2 of stage 1. So we're still in stage 1. Now we're concerned with the standard deviation. Now we need this to do a particular computation. We'll see that computation later on. But for now, it says that in that column, the referencing column, it says that we should consider figure 3. Now I have a screenshot of figure 3 right there in front of you. And in order to calculate that standard deviation, so we've got a value of 8. How did I obtain 8? Well, we have two lines on this figure. Line labeled A and line labeled B. If I've got less than 20 results, so remember how I said we need to ensure that the strength doesn't vary much across different samples. So if I've got 20, if I have less than 20 samples, then this is the line that I would be using to calculate my standard deviation. If I've got 20 or more samples, sample results, then I'd be using that line. So for the example that we're going through, the variability of strength tests comprises fewer than 20 results. It's basically 0. We don't have any. There's nothing that's mentioned in the information provided, and hence, as a result, we need to extract information from line A. How do we do that? Well, the characteristic strength has already been mentioned as 30 by the client. So all you got to do is just go up until you hit the line, which is A, and then line A is what we need, and then you go across and you read whatever value is on the y-axis, which is 8. And that's how I got my 8. So that's going to be my standard deviation. And this is going to be used to compute the mean strength across all the samples that I would take during the process of designing my mix design. So standard deviation is 8. And that's step number 2 and stage number 1. Let's move on to step number 3. Step number 3 concerns calculating the margin. Now again, we're still talking about variability in strength. So we've got a specific strength that's required by the client. So the client has specified 30 MPa as the desired strength. We in the manufacturing plant, inevitably there will be variability in strength. We can't fully control that. The best that we could do is ensure that the defective rate and the deviation in variability stays at a low rate, and that's the whole concept behind calculating, the margin and standard deviation. Now, the standard deviation was already obtained. That's the 8 from the previous step. To calculate the margin, our reference says that we have to refer to C1 or specified. In our case, the margin isn't specified by the client. We have to compute it using C1. Now, equation C1, I've extracted that again from the BRE guideline. It consists of two parameters that need to be multiplied together. So K and S. What is K? Well, K is a value that's obtained from section 4.4. And S is the standard deviation that we obtained in the previous step. So the standard deviation in the previous step was 8, and K was 1.96. How did I get 1.96? Well, if you refer to 4.4, again, it says this is the reference that's specified by the guideline. There's a screenshot of section 4.4. The defective rate is given as 2.5%. in the input that we got from the client. So the K that we need to utilize is 1.96. So it's very easy. If 10% was mentioned by the client as the effective rate, then our K will be 1.28. If it was 5%, then our K would be 1.64. In this case, it was 2.5%, and hence why we have K as 1.96. And that's what we need to fill out over here. So it's K is equal to 1.96 according to section 4.4. And to calculate the margin, we use the equation C1, and equation C1 is given over here. It's K multiplied by S, so K 1.96, which I got from here. section 4.4 multiplied by my standard deviation in the previous slide, and that's equal, my margin is equal to 16. Now, the reason that I need the margin is because I need to compute the target mean strength. As I said, there's going to be variability in the strength. The desired strength specified by the client is 30. I can get a margin of 16 in order to ensure that my the specified strength of the client is met. And to compute that target mean strength, it's just a basic addition of whatever strength was specified by the client. The specified characteristic strength, as you can see in equation C2. Now, equation C2 is referenced over here, so that's how I knew that I had to obtain information from from equation C2. So the mean strength Fm, the target mean strength, is equal to specified characteristic strength Fc, which is 30, plus the margin which I obtained from the previous step, which was 16. So 30 plus 16, that's 46 newtons per millimeter squared. So, and that's equivalent to MPa. Okay, so that's 46 MPa. Okay, so that's for stage 1. Stage 1, so that's basically, so the previous 4 steps were specific for the main strength of the concrete. Now we move on to obtaining information that would enable us to come up with the water to cement ratio, with the free water to cement ratio. Now to do that, we need to follow step 1.5 and 1.6. Now step 1.5 requires us to determine what the cement strength class is, and this is specified already by the client as 42.5. So if you go back to the information that was provided earlier on by the client, you'll see that it's 42.5, and that's why I crossed out 52.5 on the form that you have to fill out. So make sure you cross out whatever figure that you don't need. So we're left with 42.5, which is the correct one. Now the aggregate type, both coarse and fine, was specified to be uncrushed, and that's why I crossed out crushed over here. This is where we obtain our water to cement ratio. Now, and that's basically step 1.7 and 1.8. We're still in stage 1, remember. So let's talk about step 1.7 and the 0.47 that you see over here. How did I obtain 0.47? Well, again, always refer to the reference. So the reference tells us that we need to look at table 2 and figure 4. So in front of you over here, you've got table 2. I've extracted table 2 for you. Now in table 2, it specifies the approximate compressive strength of concrete mixes made with a free water to cement ratio of 0.5. So 0.5 is our point of reference for now. The free water to cement ratio of 0.5 is our reference for now. We need to extract the compressive strength that results due to the use of a water to cement ratio of 0.5. Now to do that, it's this highlighted figure here. How did I obtain that? Well, our cement strength class, if you refer to the previous steps, it was 42.5 as specified by the client. The type, of course, aggregate was uncrushed, and the compressive strength that's required was specified at 28 days. So all of this information guides us to this value that's highlighted over here. So that's the first step. This is the compressive strength of 42 that you would obtain if you were to use a water to cement ratio of 0.5. Now, this is the information that we extracted from table 2. We need to utilize figure 4, and figure 4 is what you see in front of you over here. So it does seem a bit tricky, but just bear with me because I'll explain that to you. There's several steps that need to be done over here. Let's put this box first. First of all, this is the box that I extracted from a previous step to calculate the target mean strength. So we've already done that in a previous step. But I put that as a reference because we'll be utilizing it later on. Let's first start off by looking at this information that was provided in table 2. So we said that with a water to cement ratio of 0.5, the compressive strength that we would get is 42 for a concrete mix design. 42. Okay, so how does this translate on this figure, figure 4? Well, basically you have the free water to cement ratio over here specified. So if I were to go up from 0.5, so that's the water to cement ratio specified in table 2, and I'm looking at 42, so I need to get 42 and basically to get 42 I got to travel up until roughly it's about here. So from 0.5, if I keep on going up until I reach strength 42, so that's the strength that's specified over here that I extracted from table 2, I will then draw a line, a curve, that has a shape similar to these two curves over here. Why am I interested in these two curves? Well, again, if I go up from 0.5 until I reach about 42, that's a region that's sandwiched by these two curves. Okay, so I'm trying to extrapolate basically what the curve for this specific concrete mix design would look like. It has to have a shape similar to both of these, and it has to cross this point over here at 42. So it would look something like that, the blue curve that appears in front of you on the screen. So I'd roughly, I'd just roughly sketch this curve. Again, if I go up from 0.5, I hit that blue curve that I just drew at almost 42. So you don't have to be precise. As long as it's in the boundaries of 42, you should be fine. So that's the first step. Okay, that's the first step. The second step involves utilizing this extrapolated curve, so the blue curve that we extrapolated, in order to get the 0.47. So the water to cement ratio desired for the strength for the mean strength that is specific to our client. Remember, the strength that we calculated from this table was just used as a baseline reference. Okay, so it's not the strength that's required by the client. The strength that's required by the client is 30 plus the 16 margin that we have due to variability in strength that we get from different samples. So the strength that we're concerned with is 46, not 42. So in order to determine the water to cement ratio for that strength, we need to utilize that blue extrapolated curve. And the way we do that is we start off from the y-axis now. 46 is approximately somewhere over here. Again, you need to approximately be in that region, so you don't have to precisely be, you don't have to have this done precisely. As long as you're somewhere that looks like 46, you should be all right. So 46, I'm going to start from here, go across until you hit the blue curve, so the new curve that we extrapolated based on table 2, and then I'm going to go down and I'm going to read off that value that I have on my x-axis, and that's the 0.47. Okay, so let me do this again. It's broken down into 2 steps, remember, from table 2, using 0.5 as a reference, and I know that it's 42 the strength, so I need to extrapolate that curve. It has to cross this point, so you draw the curve. Again, if I go up, hit the curve, go across, that's approximately 42, and that's from table 2. Now let's look at the information that we need to derive based on information from the client. So the target mean strength is given as 46 in our case for the example. Go across from the y-axis, that's the second step, and then go down, and that's 0.477. Okay, so that's basically how you would obtain the water to cement ratio. That's the whole purpose of stage one. It's to get to that value. Now, all the steps that led to the calculation of that water to cement ratio are very important steps. That's why you have to follow each step listed in the form precisely. So you can't jump steps. Okay, so that was for stage one. Let's talk about stage two now. So stage two relates to the water content. So we have the water to cement ratio. We need to decide on the water content in our mix design based on the workability that the client has specified. So stage two, notice that in the form, in the BRE form, stage two is labeled with the number 2, of course. So 2.1, the first step in stage 2 is to specify the slump, and it's specified by the client. So this is the information again that I gave you at the start of this example. The slump is given as something between 10 and 30 mils. So I'd specify that over here in my form. So the VEEP time, don't worry about that. We're not concerned with that. So we're more concerned with the slump. VEEP time is a measure of workability that we haven't discussed in this course. So we're just concerned with the slump. And the slump was specified by the client as anywhere between 10 to 30 mils. So that was for the first step in stage 2. Second step in stage 2 involves determining the maximum aggregate size, and again this is given by the client, so I just written down over here, I've just written down 20 mils. Stage number 3 is concerned with the free water content. Now we need to use table 3, and that's table 3 extracted for you guys from the BRE guidelines. Now table 3, it has the slump and it requires the maximum size of aggregate, and that's information that we can get from the client. So it's 10 to 30 slump, so we're concerned with this column over here, 10 to 30, and the maximum aggregate size is 20. It's uncrushed, so the value that we would be looking for is 160, and that's why I have 160 mentioned over here. So again, starting off with the slump, that's this column, 10 to 30, and it's 20 maximum size. It's uncrushed as specified initially in the example given, and hence this is the value that you would get. So the value that's basically that overlaps both of these ovals. Okay, so that was stage 2. Stage 2, now we know what the water content is. We move on to stage 3. Stage 3 is concerned with the cement content. So we already know what the water content is. That's from the previous stage, step 2.3. We have obtained the water to cement ratio from step 1.8. So it's a very simple division, 160 divided by 0.47, and you would get 340 as your cement content. Now notice that the reference says that you need to use equation C3. So I've extracted equation C3 again from the BRE guidelines. It's basically your free water content divided by the free water to cement ratio. So in this course, previously we talked about how to calculate your water to cement ratio, and we said it's the mass of water divided by the mass of cement. So if you rearrange the equation, you'd get this equation C3. Okay, so that was for the first step in stage 3. The second step in I should say the second and the third step, and also the fourth step in stage 3 concerns any modifications that we need to do to our cement content. So the minimum cement and modifications would need to be done based on information provided by the client. So in this case, a client has specified that the minimum cement content is 290. So you can see that highlighted box over here. That's information that I got from the client. 290 kilograms per meter cube. That's the minimum cement content. There's no maximum content that's specified by the client. Hence why I don't have anything over here. Now, if my previous cement content, so whatever I obtained from the previous step, was more than the maximum, then I would just stick with the maximum. But I don't have a maximum over here, so I'm only concerned with the minimum cement content. So if the minimum cement content is satisfied, and in our case it is satisfied because 340 is larger than 290, it's larger than the minimum, then we just stick with our actual cement content. In the case that this value over here, so the value that we calculated in the previous steps, if it were less than the minimum, then we need to stick with the minimum. Okay, but in this case, because it's already satisfies the minimum, 340 is more than 290, we can still stick with the value that we obtained from the previous step. Okay, so that was stage number 3. So in stage 3, we obtained the cement content. We move on to stage 4. Stage 4 involves calculating the total aggregate that will be in the concrete mix. So how do we do that? Again, in the BRE, it says that the first step in stage 4 is to specify the relative density of the aggregate. And you'd remember from talking about aggregates, SSD refers to saturated and surface dry. So your aggregate is saturated from the inside, but on the surface, it's dry. So there's no water on the surface. Any water that's present is present inside the actual aggregate. So the relative density of an SSD aggregate, and that's the best aggregate that you can get. So the best condition for an aggregate is to be at the SSD stage where it's saturated from the inside but dry from the outside. Is it known? It's not known. We have assumed that density. And how do I know this information? Well, initially when we obtained the information from the client, it was specified that 2.6 will be the assumed relative density. And this highlighted box again was given to you at the start of this example. So first step in stage 4, you need to mention the relative density. We've already done that. What's the second step in stage 4? Second step involves calculating the concrete density. So to do so, we need to use figure 5. Now you have figure 5 over here in front of you, extracted from the BRE guidelines. Now the free water content, and that's what we require on the x-axis over here. This is what we obtained from step 2.3, and if you guys remember, that was 160 kilograms per meter cubed. So 160 is going to be the value that we're concerned with. In terms of the relative densities, it's 2.6, and we've got uncrushed, of course. So we're going to be using that line to obtain the wet density of the concrete mix. So 2.6, and from 160 go up until we hit that curve, and then read across, and that's 2,400. That's your concrete density. So very simple. Again, notice how we utilize information that we've already obtained from previous steps. That's why it's important to go through that in a systematic way. You can't miss out any of the steps. Okay, step 3 in stage 4, the total aggregate content. So we've already obtained the full density of the concrete. The reference over here specifies that we should use equation C4 in order to calculate the total aggregate content. So I've extracted equation C4 for you guys. from the BRE guidelines. So D is given as the wet density of the concrete. That's what we obtained from the previous step in step 4.2, sorry. Your cement content, that's what we got from step 3.1. And your free water content, that's what we obtained from step 2.3. So if we plug in the numbers, it's 1,900. That's your total aggregate content. So step 3 of stage 4 is now complete. And that actually concludes stage 4. So stage 4, we calculated the total aggregate content. In stage 5, we move on to proportioning this total aggregate content into fine and coarse aggregates. Okay, so stage 5, the first step in stage 5, we need to specify the percentage passing, the 600 micrometer sieve, and it's 70%. How did I obtain 70%? Well, that's information that was provided to me by the client. Step 2 in stage 5, I need to use figure 6 to proportion the fine aggregate. Now, when you look at your BRE guidelines, you'll notice that there's several figure 6. So there's several diagrams that are given for figure 6, and each diagram corresponds to a particular maximum aggregate size. In our case, it's 20 mil as specified by the client. So the maximum aggregate size specified by the client is 20 mil, and hence why I extracted the relevant charts for that particular maximum aggregate size. Now we have within this diagram, we've got 4 sub-diagrams, if you like, and each one corresponds to a particular slump. In our case, remember the information given by the client specified that the slump has to be between 10 and 30. So that's the diagram that we would be looking at. So that's the diagram that I will be looking at. Now I need the free water to cement ratio, and from the previous step 1.8, we had our free water to cement ratio for the example given as 0.47. So that's on my x-axis. I go up until I hit my 70% curve. Why is it 70%? Well, in the previous step we specified that it was 70% passing the 600 micrometer sieve, and that's why it's 70%. 70% is a line that lies between these two lines that you see in front of you, so it's between 60 and 80. So it has to be somewhere in that region. Again, you don't have to be exactly precise. That's why my red arrow stopped midway between 60 and 80. And if I go across, so that's where I predict my 70 would be. If I go across and read the y-axis, it's about 27. That's why I've got 27% over here. So that's step 2, stage 5. Steps 3 and 4 are associated with the fine and coarse aggregate respectively. Now the guideline says that I have to refer to equation C5. I have extracted equation C5 for you. So for fine aggregate content, it says that it's the total aggregate content multiplied by the proportion of fines. In order to get the coarse aggregate content, I have to know what my total aggregate content is from a previous step, minus my fine aggregate content, which I would have calculated from this equation over here. So let's do it. For 5.3, my fine aggregates, step 4.3, 1,900, that was my total aggregate content, multiplied by 0.27. The 0.27 is what I obtained from step 5.2. In step 5.2, it was 27%. That was specified. So that was, the aggregate content that was passing that small sieve. So 27% as we obtained from step 5.2. And if I multiply both of these together using this first equation, we obtain the fine aggregate content, which is 515 kilograms per meter cubed. For the coarse aggregate, again, starts off with the total aggregate content as specified in this equation, minus whatever you obtained from that calculation in 5.3, which is 515. So 1,900, take away your fine. So total, which is 1,900 aggregate minus fine, you're left with your coarse. Okay, because you remember your total aggregate, which is 1,900, is composed of two things. It's composed of your coarse and it's composed of your fine. Okay, so that was for steps 5.3 and 5.4. Let's move on to the final step in stage 5. The final step is associated with proportioning your coarse aggregates into the two sizes. Now, a recommended rule is to associate a third, or to divide your coarse aggregates via this ratio. So 1/3 10 mil coarse aggregates and 2/3 20 mil. So there's more larger aggregates compared to the smaller sized ones for the coarse aggregate itself. And the way we do that, well, if you look at your 10 mil coarse aggregate over here, 460, that's rounded to the nearest 5. So it's 1/3 multiplied by 1385. So that was the 1385 was the value that we obtained from the previous step. And that was associated with your coarse aggregate. So your total coarse aggregate was given as 1385. A third of it is going to be 10 mil coarse aggregate, which is 462. If you round up to the nearest 5, that's 460. And 2/3 of the coarse aggregate will be associated with 20 mil, will be made up of 20 mil coarse aggregate. So 2/3 multiplied by 1385, that's 923. And that equates to 925 if we round up to the nearest 5. So the overall output that you would get, your cement is 340, your water is 160, your fine aggregates 515, and then you have your coarse aggregates split into 10 mil and 20 mil, so that's 460 and 925. Okay, so in summary, in today's lecture, I went through the 5 stages that are involved in normal concrete mix design. As I said, it's a systematic process, so just make sure that you follow the steps that are specified in the BRE guideline. You guys have now access to the BRE guideline on Moodle. And the easiest way for you guys to figure this process out is to watch this tutorial or this lecture several times and fill out the form, right? So the form, I think it's on page 11 of the document, and page 16 in the PDF file. So on the top of the document, you'll see 11 for the form. So that's where you find the form, on page 11 of the document. But if you look at the pages, number of pages given in the PDF file that I've extracted for you guys, it's page number 16, right? So this is where you find the form. Just fill out the form and make sure you do it in the steps specified. And yeah, that's basically it for this week's lecture. And we have now successfully concluded the concrete part of this materials course. Starting from next week, we'll be talking about a different material. So we've got 3 more weeks left in this course, and each week in the remaining part of this course, we'll be discussing one separate material. So we've got steel that we need to talk about, and that's going to be 1 week, and then we have masonry, and then final week we'll be talking about timber.